All right, so this is basically where we left off last time, right? We learned how to calculate the change in entropy for the surroundings using a specific equation, right? And we also learned how to determine the sign of the entropy change for the system, as well as the meaning of the entropy change for the universe, right? So if the value or the sign of delta S universe is positive, then we have a spontaneous reaction or spontaneous process. All right, so let's take a look at this example again. We have a combustion of propane gas into carbon dioxide and water. And this is basically an exothermic reaction because it's releasing heat at the amount of 2044 kilojoules. So calculate the entropy change in the surroundings when this reaction occurs at 25 degrees Celsius. So the equation that we learned last lecture to determine the change in the entropy for the surroundings is given by this. Okay, so we have delta S surroundings is equivalent to the negative of the change in enthalpy for the system divided by temperature. Right? So we're given the value of delta H reaction here, which is basically the delta H of the system. And so that's equivalent to the negative of negative 2044 kilojoules divided by the temperature, which is in kelvins. So we're given temperature here, 25 degrees Celsius. Convert that into kelvins, and we have 298 kelvins. So here we get 6.86 kilojoules per Kelvin. All right, so that means that delta S of surrounding is positive. All right. For part B, determine the sign of the entropy change for the system. So how do we determine the sign for the entropy of the system? You guys remember? Right, so you would have to compare the number of moles of the reactants from the products. So for the reactant side, we have a total of 6 moles. And in the product side, we have a total of 7 moles. So because there's an increased number of moles, the change in entropy for the system is going to be positive. All right, so part C is going to be pretty simple in that case because we know the equation for delta S universe, and that's equivalent to the sum of the first two, right? So delta S surroundings plus delta S of the system. So since both are positive, you're adding 2 positives. So that means the delta S of the universe is also going to be positive. So would this be a spontaneous process or non-spontaneous? All right. What did you say, Charles? Spontaneous, yes. All right, so that's basically where we left off last time. All right, so today we're going to learn about a new concept called Gibbs free energy, right? And this is a free energy because this is the maximum amount of work energy available that can be released to the surroundings by a system. And this is at constant pressure and temperature. And Gibbs free energy is also known as the chemical potential, and it also helps us predict spontaneity, similar to delta S universe, right? So for delta S universe, being positive gives you spontaneous reaction. If delta S universe was negative, then that would be a non-spontaneous process. So let's take a look how the change in Gibbs free energy can help us determine spontaneity for a process or for a system. So we learned these two equations right here. We have delta S universe equation and delta S surrounding equation. So if we substitute the delta S equation, delta S surrounding for the delta S universe equation, we get a new equation for delta S universe. All right, so we have delta S universe equals delta S of the system plus negative delta H of the system, which is the change in enthalpy for the system, divided by T. Okay. And so we can simplify this equation by multiplying both sides by negative T. So we can get rid of that denominator, which is temperature. Right? So we can multiply this side by negative T. We can multiply this side also by negative T. All right, so then this becomes negative T times delta S universe equals negative T times delta S system. And then notice the negative here will cancel with this negative. It'll basically turn into positive. And then the temperatures will also cancel, leaving you with plus delta H system. Okay, and this function right here is the change in Gibbs free energy. Okay, this is equivalent to delta G. So delta G now becomes negative T delta S system plus delta H of the system. All right, so as you can see here, delta G, the change in Gibbs free energy, is dependent upon three factors, right? Three variables. One is temperature, second one is delta S of the system, and the third one is the change in enthalpy for the system. All right, so again, if delta S universe was a negative number, a positive number, delta S universe greater than 0, being positive means you have a spontaneous process. All right, and so if we have the equation for delta G relating delta S universe and delta G, right? If delta S universe is spontaneous, right? If it's positive, then what would be the sign of delta G?
Negative.
It would be negative because you're multiplying it by a negative temperature. And temperature is in kelvins, and it's always going to be positive, right? Because the lowest temperature possible is 0. All right, so that means that delta G is going to be negative for a spontaneous process. All right, so make sure you don't get those two confused. So delta S universe has to be positive in order for the system to be spontaneous, or the process being spontaneous, and delta G has to be negative for the process to be spontaneous. Okay. So you just have to remember the relationship between the change in Gibbs free energy and the change in the entropy for the universe. So if you know that relationship, then you'll be okay on the test. All right, so here's a cleaner version. Okay, again, when delta S universe is positive, being spontaneous, then delta G has to be negative.